Airplanes are wonderful things. They fly through the air and move people and goods at rapid speeds around the world. However, they have some downsides. In order to take off and land, an airplane requires an enormous amount of land for runways. So for over a century, aeronautical engineers have been trying to create a vehicle that has all of the strengths of an airplane, but could take off and land like a helicopter. And they've kind of done it. Learn more about vertical takeoff and landing aircraft and the challenges in designing them on this episode of Everything Everywhere Daily.
Hey, I'm Ryan Reynolds.
Recently, I asked Mint Mobile's legal team if big wireless companies are allowed to raise prices due to inflation. They said yes. And then when I asked if raising prices technically violates those onerous two-year contracts, they said, "What the f*** are you talking about, you insane Hollywood ass?" So to recap, we're cutting the price of Mint Unlimited from $30 a month to just $15 a month.
Give it a try at mintmobile.com/switch.
$45 upfront payment equivalent to $15 per month. New customers on first 3-month plan only. Taxes and fees extra. Speed slower above 40 gigabytes. See details.
This episode is brought to you by Indeed. When your computer breaks, you don't wait for it to magically start working again. You fix the problem. So why wait to hire the people your company desperately needs? Use Indeed's sponsored jobs to hire top talent fast. And even better, you only pay for results. There's no need to wait. Speed up your hiring with a $75 sponsored job credit at Indeed.com/podcast. Terms and conditions apply.
If you ever look at a satellite image of a city, you can usually spot the airport pretty easily, regardless of the size of the city. And that's because airports and runways are huge. Large aircraft require long runways. Airports and runways are so large that they usually have to be placed on the outskirts of cities. All of this is required because of the way airplanes work. They have enormous engines to provide thrust, and then use airfoil wings to provide lift once they can get to a high enough speed. This is how the very first mechanized flight by the Wright brothers worked, and it's still how most aircraft work today. However, ever since the dawn of aviation, aviators have wondered if they could just take off and land without the use of a long runway. They imagine the possibility of just flying into the air vertically, or at least with a much smaller runway. The first step in the direction of this was the development of the autogyro. An autogyro is a type of rotor craft that uses an unpowered, free-spinning rotor for lift and a conventional engine-driven propeller for forward thrust, allowing it to take off in short distances but requiring forward motion to stay airborne. While they can take off in a short distance and land almost vertically, they still required some forward motion and were not true vertical takeoff aircraft. True vertical takeoff was realized with the first controllable helicopter. It was developed by Igor Sikorsky's, whose VS-300 prototype in 1939 introduced the now standard configuration of a main rotor with a tail rotor for stability. Helicopters solved one problem, but they had a host of limitations. While helicopters are highly maneuverable and capable of hovering, they suffer from significant drawbacks in speed, range, and payload capacity. The fastest production helicopter ever made could only reach speeds of about 400 kilometers per hour or 250 miles per hour. Likewise, most helicopters can't operate much beyond 10,000 feet in altitude and have a very limited range. Vertical takeoff and landing aircraft, also known as VTOL, were designed to combine the best aspects of both fixed-wing airplanes and helicopters. One of the biggest drivers of VTOL development was military necessity. During the Cold War, military planners recognized that runways were highly vulnerable targets in a potential conflict. Traditional fighter jets and bombers required long, well-maintained runways, making them susceptible to enemy attack. VTOL aircraft, on the other hand, could operate from small improvised airstrips, roads, or even ships, significantly improving their survivability. Another reason for pursuing VTOL development was the need for increased range and fuel efficiency. Helicopters are highly inefficient over long distances because they rely entirely on the main rotor for lift, which requires constant power. Fixed-wing aircraft, however, generate lift more efficiently using their wings, reducing overall energy consumption. It wasn't until after the end of the Second World War that VTOL development was taken seriously. The first design concepts were known as tail-sitter aircraft. Tail-sitter aircraft are a type of VTOL design that take off and land in a vertical position, resting their tails when stationary and transitioning to horizontal flight once airborne. These aircraft are equipped with powerful engines or propellers that generate enough thrust to lift them directly off the ground. Once airborne, they gradually transition by pitching forward into level flight, where conventional aerodynamic surfaces such as wings and tail fins take over for lift and stability. For landing, the aircraft reverses the process, tilting back to an upright position and descending vertically onto its tail. Several early models of tail-sitter aircraft are developed in the late 1940s and early 1950s, mainly as experimental military projects exploring new VTOL capabilities. One of the earliest examples was the Convair XFY Pogo, a U.S. Navy prototype powered by a turboprop engine with large contra-rotating propellers. Designed to operate from small ships without the need for runways, the Pogo demonstrated the feasibility of tail-sitter flight, but proved difficult to control during the transition phase. Another notable design was the Lockheed XFV Salmon, which featured a similar VTOL concept, but it used a more conventional-looking fuselage and twin vertical stabilizers that became horizontal in level flight. The Ryan X-13 Vertijet, an experimental jet-powered tail-sitter developed by Ryan Aeronautical, further explored the concept with a pure jet propulsion system. It successfully demonstrated vertical takeoff, transition, and landing, but the operational challenges of precise control and pilot visibility made it impractical for military use. One of the most unique designs was the French-made Coleopter. It was an experimental tail-sitter VTOL aircraft designed to take off and land vertically while transitioning to horizontal flight using a circular wing structure. Here I should note that the transition from vertical to horizontal flight was to be the major problem with every VTOL design. Lifting up vertically isn't that hard so long as you have enough power. Likewise, horizontal flight isn't a problem so long as you have the speed. However, going from vertical to horizontal turned out to be a very challenging problem. The next big design was the tilt rotor. Tilt rotor aircraft are a type of VTOL aircraft that use rotating engines or rotor assemblies to transition between vertical and horizontal flight. At takeoff and landing, the rotors are positioned vertically, functioning like helicopter rotors to generate lift. Once airborne, the engines are gradually tilted forward, allowing the aircraft to transition to conventional fixed-wing flight, where lift is generated primarily by the wings rather than the rotors. This design combines the vertical takeoff and landing capabilities of a helicopter with the speed, range, and efficiency of turboprop airplanes, making tilt rotors particularly useful for military and transport applications. One of the earliest tilt rotor concepts was the Bell XV-3, developed in the 1950s by Bell Aircraft. It served as a testbed for the tilt rotor concept, successfully demonstrating the transition between vertical and horizontal flight, but its technology was not yet mature enough for operational use. Another early design was the Canada Air CL-84 Dynavert, a tilt-wing aircraft developed in the 1960s, which featured an entire wing that rotated to enable vertical flight. Although it performed well in tests, it never entered mass production. The most significant breakthrough came with the Bell XV-15, an experimental aircraft developed in the 1970s that refined tilt-rotor technology, proving its viability for operational aircraft. By the late 1970s, everything was still experimental regarding tilt-rotor aircraft. No tilt-rotor aircraft had gone yet into mass production. The United States military recognized the limitations of helicopters, particularly their relative slow speed and short range, which made them vulnerable in combat zones and inefficient for long-distance operations. The 1980 failure of Operation Eagle Claw, a helicopter-based mission to rescue American hostages in Iran, highlighted these weaknesses and accelerated the push for an aircraft that could combine the vertical lift of a helicopter with the cruising speed of a turboprop plane. This need led to the Joint Service Vertical Takeoff Landing Experimental Program initiated in the early 1980s, with Bell Helicopter and Boeing collaborating to develop what became the V-22 Osprey. The V-22 faced numerous engineering and developmental challenges throughout its design and testing phases. One of the most difficult aspects was perfecting the tilt rotor mechanism, which required complex engineering to transition smoothly between helicopter and airplane modes, all the while ensuring stability and control. The early prototype suffered from serious mechanical failures and software issues, leading to several high-profile crashes. In 1991, an early Osprey prototype crashed due to hydraulic system failures, killing several crew members. A 1992 crash caused further concerns about safety and reliability, leading to extensive redesigns and system overhauls. The most devastating incident occurred in the year 2000, when a V-22 crashed during a training exercise, killing 19 Marines. Investigations revealed issues with flight control software and pilot training, leading to further delays and extensive modifications. The aircraft's complex tilt rotor system made it mechanically intricate and expensive to maintain, with high maintenance costs and reliability issues continuing even after it entered service. Additionally, the F-22 has struggled with something called vortex ring state, a dangerous aerodynamic condition that can lead to loss of lift in certain flight conditions, contributing to past accidents. Despite its troubled development, the F-22 Osprey was eventually declared operational in 2007 and has since become a crucial asset for the U.S. Marine Corps, Air Force, and Navy. It's been used extensively in combat and humanitarian missions, proving its value in rapid troop deployment, medical evacuation, and long-range special operations. There is a civilian tilt-rotor aircraft which is looking to be certified for civilian use, the Leonardo AW609. It's been in development for over 20 years, and it's hoping to finally receive certification sometime in 2025 for commercial use. There is one other type of VTOL aircraft that has found its way into active use: direct lift jets. Direct lift jet aircraft are in many ways easier to engineer. They don't require complicated tilt mechanisms where the engines have to move while in flight. All you're doing is redirecting the jet exhaust down instead of out the back of the plane. Several early experimental designs in the 1950s, such as the Rolls-Royce thrust measuring rig and the short SC-1, were developed to test vertical lift using jet engines, but most of these were impractical due to high fuel consumption and control difficulties. The Harrier jump jet became the first successful operational direct lift jet and remains one of the most iconic VTOL aircraft ever built. Developed in the 1960s by Hawker Siddeley in the UK, the Harrier was designed to operate without the need for large airstrips, making it highly adaptable for both land-based and naval operations. The key to its VTOL capability was the Pegasus turbofan engine, designed by Rolls-Royce, which used 4 vectoring nozzles to direct thrust downward for vertical takeoff and landing, then gradually transition to horizontal flight by redirecting thrust rearward. Unlike previous VTOL jet designs, which struggled with balance and maneuverability, the Harrier used reaction control jets for fine adjustments during hover, significantly improving its handling. The Harrier entered service with the Royal Air Force and then later the U.S. Marine Corps, where it became a crucial asset for close air support, reconnaissance, and naval strike missions. It saw significant combat use, most notably during the Falklands War of 1982, where its ability to operate from short runways and aircraft carriers gave British forces a decisive advantage. Despite its success, the Harrier faced several challenges, including high pilot workload, maintenance complexity, and fuel inefficiency in VTOL mode. These limitations led to continued development, resulting in more advanced variants such as the AV-8B Harrier II, co-developed by McDonnell Douglas and British Aerospace, which featured improved avionics, greater payload capacity, and more powerful engines. VTOL aircraft are still being developed. One of the newest planes is the Lockheed Martin F-35B Lightning II. The Lockheed Martin F-35B Lightning II is a 5th-generation multi-role stealth fighter designed for short takeoff and vertical landing capabilities, making it the most advanced VTOL-capable aircraft in existence. Developed as part of the F-35 Joint Strike Fighter program, the F-35B was created to replace aging aircraft like the Harrier jump jet, offering improved stealth, avionics, and combat performance while retaining the ability to operate from small carriers and small airstrips. The F-35 program will be the topic of a future episode. Vertical takeoff and landing aircraft have come a long way from experimental designs to mainstay military and civilian applications. Innovations continue to push boundaries, which means it'll probably be a permanent fixture for military use and perhaps will have even greater use in the future for civilians. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Benji Long and Cameron Kieffer. I want to give a big shout out to everyone who supports the show over on Patreon, including the show's producers. Your support helps me put out a show every single day. And also, Patreon is currently the only place where Everything Everywhere Daily merchandise is available to the top tier of supporters. If you'd like to talk to other listeners of the show and members of the Completionist Club, you can join the Everything Everywhere Daily Facebook group or Discord server. Links to everything are in the show notes.